So welcome to How Things Work, Physics 1050. I'm Lou Bloomfield. I've been teaching variations of this course now for over 20 years, which is kind of amazing, but okay. I'm delighted to have you here, and I'll get started. So, just to begin with, I'll give you, this will listen to me. Come on. Waiting for what? There we go. Okay. Little introduction to the class and basically the whole concept behind it. Let me start off by talking briefly about physics. What's physics? For some of you who've taken it, we'll get to that. You've taken physics and hopefully remember something from it. For those of you who haven't ever encountered physics before, it's basically the study of the physical world. And the idea is really to look at how the universe works, from the smallest scales to the largest scales, what makes everything happen, and to learn how to use what you've learned to predict things. I mean, to an extent, the universe is predictable. You know if you do this, this, and this, that something specific will happen. There are limits to how well you can predict the future, even if you know everything, but nonetheless, there's a system to how things happen in our world, and this is the study of that. From a more ordinary language, it's answering the how and why questions about the world around us. So it's not the what, where, whens, it's rather how does this happen or why does this happen? And I view it, at least, as a key component of science literacy. So for many of you, for most of you, you're not science majors. This is something, in fact, an enrichment course. But hopefully it'll be something that you actually find useful in your everyday life, now and forever. So my goal is to give you something of value to you, not to have you come and obtain something of value to me. And if I don't manage to do that, I haven't fulfilled my own mission. So this should be about you. Physics in general is woven throughout everyday life, modern life in particular. It's the heart of most technology these days, which is becoming more and more central to existence, for better or worse. And physics will play a key role in dealing with lots of issues that are current now and will become more and more important in the future. I mean, things like energy issues, which you're well aware of, but actually resolving them and dealing with them in an intelligent way requires some understanding of what energy is and how it moves around and things like that. So you will be dealing with real physics problems in your lifetime, whether you like it or not. You might as well have some understanding of what underlies those questions, those issues. Now, the How Things Work class, there's a long story behind why I decided to start teaching it 20 years ago, but it's physics in the context of objects. So how things work, it's things, real things. It's actually what drew me to science in the first place. I liked stuff, playing with stuff. I don't need to own it all, but I like to play with it. Always did, and so that's how I got hooked on science. We will do that. We'll play with objects, real objects that you presumably care about, at least to some extent, and find within those objects physics concepts. And find within those physics concepts, sometimes, formulas. That's the reverse of the traditional pattern, which is the conventional course, which I guess I always call physics for physicists, no matter who it's taught to. The conventional course it starts with formulas, or pretty much. The first thing that's thrown at you somehow in those courses is a formula, and living on top or beside that formula is some concept. And if there's time at the end of the class, the end of the semester, or maybe the second semester, there are applications to it. So it's pretty irrelevant. And my point is to make this relevant. It's, in effect, the case study method. So people who teach whatever they teach, they sort of follow traditions. And the tradition in physics was this classic formula and recipe following tradition. I shouldn't say recipe following, but formulas. And there are other disciplines where case study became the tradition, notably business school. And so, okay, I'm using the case study in physics, and hopefully you'll agree with me that it works reasonably well. It is answering the how and why questions. So you'll see as we go through the semester and we start dealing with real objects, how a bicycle works, we'll ask the how and why questions. How is it possible to stay up on a vehicle that has only 2 wheels? Isn't that stupid? I mean, a two-legged chair is not much of a chair, or a stool even. So we'll answer those how and why questions. And really, this is how science was discovered. It wasn't done principle by principle, like this week we're going to invent that principle, and that week, scientists even wanted to answer specific questions about real life stuff. So we'll revisit that world. My goals in teaching all this to you, or trying to teach it to you, is I'd like you to develop real understanding and intuition about the world around you. So in places where you sort of see it as maybe magic or willy-nilly and unpredictable, you'll have some sense of how it isn't, or to the extent that it is, why it is. The machines and gadgets of the world around you are not magical. They do what they do for good reasons, and to a large extent we can explain those reasons in ways that you can understand. What else here? Hopefully you'll come out with some appreciation of that physics isn't just this academic, irrelevant discipline that physicists do and everybody else can completely ignore. The universe is predictable, not magical. That's basically, I've already said that. And hopefully you'll come away actually kind of liking parts of the science. It's not so bad. You will find that this class is relatively non-mathematical, and that's good news, bad news. It's, for those of you who are scared to death of math, maybe it's good news for a while. In my experience, the people who have had very math-focused physics classes talk about hating the math, but secretly they love the math because they don't have to think. They can just put in the values into the various equations, turn the crank, and out comes an answer which might well be rewarded with 100% or an A. Hey, this is good. I didn't do anything except I got an A. So I don't do a lot of the math. You'll find that, for example, on a homework assignment or an exam, just about the only number that shows up that's interesting is 0. It's kind of the only interesting number. All the other ones are special cases. 0 is special. Okay, so 0 will show up a lot. What do I expect you to do? I do expect you to think. And this is difficult. It's difficult for everybody. It's particularly difficult for people who have tried to get by without doing it very much. You can judge for yourself if that's you. You have to actually learn the concepts and really suffer over them. That's why we'll have homework assignments and exams, is to get you thinking. I focus on the concepts rather than the formulas. And here again, that leaves the math out by and large, but it means the concepts are right there, front and center. You can't get past them without well, you can get past them without understanding, but it's not very successful. Okay? Please understand them. Work at it. We'll talk about how to do that. I assume no prior study of physics. In my experience, it doesn't make a lot of difference for many people, whether they've had 1 or 2 semesters of high school physics. You'll see. Those of you who have, great. You may find yourself encountering things in a way you haven't seen them before. Last bit on this slide is that I teach 2 courses, right? Physics 1060, 1050. It's a spring version, a fall version. They start out the same and then they diverge. And they diverge in such a way that you can take one or the other or both in either order. So people who've taken 1060 before, and there are a fair number of you in here, you get 2 weeks of review. You get to see things you've seen before, listen to jokes you've probably heard before, just don't tell the punchlines. And then it'll diverge. So in my experience, no one ever, well, it was never a bad thing to do the review. Okay, you may find it dull, but okay, it's important. Now, clicker questions. I should say early on, I won't start counting clicker questions until Monday. This is to get you guys active during the class. Education, higher education included, is evolving very fast. And among many things is that the push towards more and more active classrooms is happening. And so I want to keep you guys engaged, and the more the better, but we'll see how much I manage to do. But it's okay. Starting Monday, I'll ask questions and expect you to respond to them with gadgets that look either like this. This is the iClicker 2. This is a blue version of the iClicker 1. It doesn't matter, either one of these. Eventually, we need to get your iClicker registered to you so that this receiver up here knows it's you clicking in. But the real value of this, I mean, you all can think this is obtaining credit and stuff. The value to me is to keep you thinking. Okay? So for now, this doesn't count for anything. I just want to ask a couple questions today, and tomorrow, Monday, we're real. Oh, incidentally, I have a little fleet of these guys that I'll loan out if you forget one. Come on up, and you can borrow one at the beginning, before class. The one other thing is that some of you may have old iClicker ones that have lost their little code. I can determine it with the receiver. So come and see me before or after class, and we'll figure out what the code is. The iClicker 2s cleverly tell you what their code is in their little display. Okay, with all that, we can ask the first clicker question. If you got a clicker, great. If you don't, so what? What's your background in physics? Simple question. I've given you 5 choices, and I can make it so you can see it better. And to start, they changed the software. This should work, right? Is that starting it? Yes. Okay. So now you can all click in, and 65 people clicked in, 73, 75. Wow, this is pretty good. All right. And typically, I give you 60 seconds. I won't go that long this time. But if it's a question, if I ask you a question that really takes some thinking and maybe even some conversation with your neighbors, we'll let it go longer. Because part of if all I do is talk up here and you all listen, this could be just a tape recording up here, and I could go away. So you have to get the back and forth going. Conversation is good. Okay, looks like we've reached a limit here, so I'll press the software upgraded here, so I haven't seen these words like stop before. That's kind of, and display the graph. There we go. Okay. The vast majority, I mean, yeah, plurality. Taken 1 year of physics. Okay, so a lot of you, and that may scare those of you who have never taken physics, and a few of you are Olympic gold medalists here. This is great. We got 4. That beats UVA swimming, but not by much. All right. So, that's useful. That actually is that's the norm. That's what I always encounter every year for the past couple of years when I've asked that question. It's about right. Another question to ask you is more specific. So those of you who've taken physics, and even if you haven't, whatever, the medalists should certainly be able to answer this. Can you distinguish? Now I'm giving you pairs of physical quantities. These are things that mean something in the world of physics. Can you distinguish those pairs? So velocity, acceleration. Can you distinguish mass from weight? Can you distinguish force from momentum? See what you think. With each passing year, people get more comfortable with technology. The stuff comes in faster. Like, I press the start button, everyone's in. It's kind of amazing. All right. Incidentally, we're not allowed to have any fun in this class. Okay. So, sweeping up towards, the majority, well, not a majority, but people are pretty comfortable on average with those concepts. So we will revisit all of them this week and next week. So hopefully you really have some familiarity with them. And when we're done, hopefully you'll really all feel very comfortable with them. All right, so some things to do. So finishing up this introduction then. Read the syllabus. This year, for the first time in a long time, I actually printed a version of it, which is on this chair up here. So pick one up before you go out. Please read it. It's hard for me to deal with the people, like the guy last year who called me up from some party for his mother in Richmond, asking whether the exam that he had just missed, what could we do about that? Because he had not known there was a midterm exam. I don't like dealing with that stuff anymore. It says in the syllabus when the exam is and what the consequence for missing it is, which is a 0, okay? So, please read it. Second thing, please read the textbook or equivalently the ebook that's associated with Wiley Plus before each class. Why? Okay, I wrote it. I like the idea of you all reading what I wrote. Okay, but mostly physics is actually hard, even for physicists, and you have to go through it several times. So the concepts that aren't obvious, well, the first time you pass through some of these concepts, they will just go right past you, and you won't learn them. You won't really get them in your gut, at least. And so revisiting them is important. And part of that is it would be best if your first encounter with some physics concept is not in this class, because then you're not ready to ask any question. You're just catching it for the first time, and it doesn't settle well. So please read ahead, and I will try to encourage that through the use of clicker questions that are focused on the reading. So some of the clicker questions will actually ask you, in effect, did you read it? The assignments, the coursework for the class, which is on this syllabus, but I'll tell it to you, 10 problem sets plus an opening sort of test run. The 10 problem sets will come up pretty much once a week, due on Mondays, almost always. And the goal of these, for my purposes, is to get you thinking through the material we've more or less just done. Because if you just listen to me say it, or read it from the book, it doesn't really settle until you work with it. You work with these concepts. So that's what the problem sets are to do, to get you working with the concepts. 2 midterm exams, one late in September, one right at the beginning of November, both on Fridays, and then there's a final exam. And there's a portion of your grade, as I emailed you. You'll see I email out customized emails a lot. Okay, not too much. I don't want to fill your email box with them, but participate in class. So 10% of the score is associated with these clickers, and just thinking here with us and getting involved in the class. All right? I think I've got one more slide here before I'm done. Yeah. So, do ask questions and volunteer in class. The class is most functional when it's conversation rather than just me throwing at you and you trying to catch, hopefully. So, let's get it going. It takes a lot of work on both our parts to keep that happening. I'll try to keep up my energy and keep pestering you all to ask questions. And, okay? Do the demonstrations yourself after class. You'll see this semester in particular, a lot of demonstrations. It's a much more mechanical focused semester than the spring semester, so I've got lots of things that you can just see. You see the physics right there. Sometimes seeing it isn't believing it. There are some demonstrations where you can see it happen, but it doesn't sink in the same way as doing it. So I totally encourage you to come up after class and try some of these things. They're more real when you do them. I'm happy to help you and all that with the demonstrations. What else? Talk to me and come to my office hours. Now this is my big harangue. 20 years ago, people came to office hours, and they would talk to me. These days, okay, my hair is a little grayer than it used to be. But the main thing that's happened is people are lost in these little guys, right? So is there another human being at the other end of this? I don't know. But it's sure comfortable. And my perception is that people in your generation, I won't name you, but have struggle with dealing with people who make you the least bit uncomfortable. It's much easier to put them at the other end of some gadget. So, okay, we do have a teaching assistant in this class. Matt is up here in the front. So Matt is, yeah, stand up, come here. Matt Kaplan is, yeah, sure.
Thank you for the introduction. I get a mic, sweet. Hey, hope everyone can hear me in the back. This makes me uncomfortable.
There.
Thank you. Hey, my name's Matt Kaplan. I am a fourth-year physics major, and I'm the TA for this class. I will be available in the physics room 220. That's the office hours room. It's right down the hall. It's got the tables, a bunch of chalkboards on the room. I'll be sitting in there a bunch of hours during the week. Haven't decided yet, but you'll get an email, and it'll go on the website. And basically, I'm just another resource that's available for you for this class. If you have a question or need a concept explained to you, even if you're struggling with a homework problem, come to me. You know, I'm not scary, I don't bite, but I can help you with the homework problem. I'm not going to give you the answer, but I'm another resource that's available for you, so take advantage of that. Thanks.
So, do seek help. Don't sit and suffer on your own over the questions. The point is to get them right, not by having your friend give you the answer, but by suffering on them until finally you understand them. And so go talk to Matt as one choice, and come talk to me as another choice. Again, I don't bite either. So if you go through your 4 years here basically not knowing any of the instructors, whether it's me or whether it's anybody else, you've missed something. And it's easy to do that. There are plenty of people who go through 4 years. I get people asking me to write letters of recommendation for them in their 4th year. And they were some of the ones who never talked to me once. And all I can do is say, well, you know, this person was in my class, but I don't know them. So please, come and talk to me. That's why I have office hours. Before and after class is fine too. Okay? All right. Coursera. This summer, the university joined an online, life's changing, right, in education. As of a couple of years ago, online courses appeared, were developed in various ways here and there. And there are a couple of major companies. They're not huge, but they're the leading companies that are trying to offer classes to basically the whole world. At present for free. In long term, free is a difficult thing to it's hard to do things for free, right? People have to eat, okay? But in the short term, the universities in this country, a few of them are beginning to offer courses essentially to the world for free. And I'm one of the test pilots for UVA. So there are 3 of us in the College of Arts and Sciences setting out to teach these massive online open courses, MOOCs. And so the enrollment in my class, still not, the starting date hasn't been set. It will look a lot like this class, except that it will be more like television and less like live lecture. The current enrollment as of this morning just crossed 15,000. This is without a starting date or a duration. It's going to be quite an adventure. But I'm going to begin collecting material for this class now, which is why I have a camera over there. Hi. Over there. I'm trying to get somebody to run the camera so it's not just sitting there just, you know, anyway, this is my problem. But in any case, I'm working towards getting ready for this course. And actually, if those of you who are sort of media type people and interested in helping me, working with me on this, I would love to talk to you. Okay? I've done, as you probably will see, I've done a fair amount of television in my time. And so I'm looking at this as kind of like making low budget television. High budget television. I've done some high budget television, which is kind of fun because you get to do things like I got to drive a Lamborghini as fast as I could around a closed course for a whole day. I'll try to bring in some of the videos as they become relevant, or maybe even if they aren't relevant. But whatever. Anyway, so Coursera, here we come. It's in the future, pressing. Okay, this room is open before and after class. I have set it aside so that the hour before, the hour after, you can come in, you can stick around, play with the demonstrations, and particularly afterwards. talk to me. This is, don't just, if you have to zip out to go architecture studio or whatever it is, I understand totally. But to the extent you can stick around and do things, more, you get more than you pay for, right? It's good. All right. Education is one of the weird things where many people are happy to get less than they paid for. Oh, he canceled the class. Yes. Okay. I haven't canceled the class. During class, if you have to come and go during class, it's fine. Through the back doors is probably ideal, because sometimes somebody coming right across in front of me, which happens. There's behind me, but in front of me is more fun. It's a little, it rattles me if nothing else. In general, it doesn't rattle. This stuff doesn't rattle me. This stuff does. There are more stories, but okay. And the last thing, electronic devices. I ask you all to put them away. I mean, okay, they're there. It's so tempting when you open up this device. You know this, right? It's an entertainment center. And unless you turn off the wireless or something like that, you're just peppered with fun. And it's going to be more fun than me. And the other thing is, okay, you might be able to survive this, but this wedge of people behind you, they get drawn in. Sometimes I look up in the audience, you all, and I will see a computer, and I will see these eyeballs going back up in about, is it 45 degrees? That's more interesting than him. And okay, please don't do that stuff, okay? As you will see, I get bad at enforcing it after a very short period of time because I cannot multitask. And so if I try to play policeman, I fail. But, okay, enough said. Any questions? Okay, now I've done exactly what I said not to do, which is just like me talk at you. Questions? Things you care about? The Red Sox. No, I don't know. Okay, all right, code of silence. First topic. Where is it? On to physics. So the first topic for a number of years has been skating. I'll start off with a question. You'll see the pattern. Those of you who took Physics 1060 know my pattern. The pattern is I'll ask you an introductory question, just sort of set the stage, and then I'll look a little bit at the object, sort of figure out what the how and why questions are, and then we'll go through the how and why questions one after the next. So that's the structuring. I do have my lecture slides. They evolve over the semesters and stuff. I have posted an early version on the web. You can print them out, either black and white or color, and you can use those to the extent if they save you from just mechanically transcribing what I say, great. If you need the act of writing to remember and learn things, then do that. In any case, you have some early warning of where we're going. So, skating, I'll ask the introductory questions. So this is just to set the stage. And this is the question. It's a rotary lawnmower. And hopefully you know, I should have a picture up here of what a rotary lawnmower is. Basically, almost every lawnmower you've ever seen is one. It's got a blade that spins around underneath a protective shroud. And as it goes along, it cuts the grass. And the grass comes out relatively even, and the little flinders go off and do what they want to do. The question is, if those grasses were not attached to the ground, had no roots, could this spinning blade still cut them? Any questions about the question? You okay with it? Those of you who have clickers, see what you think. And actually, you're welcome to talk to each other on this. So a lot of times when I ask a question, there's value in exchanging thoughts with each other. Nothing else, you get to meet the people next to you. Okay. 5, 4, 3, 2, 1. And we'll see what. And now with these introductory questions, I don't answer it yet. So I'll show you what people think, and we'll come back to it when we've explored the physics that makes it hopefully relatively easy to answer. So we're about 2 to 1 in favor of no, that the attachment of the grass to the ground is important. Okay? All right, well, so now just finish setting the stage for talking about skating. And why did I pick it? It's because it's an illustration of one of I guess, the simplest, although not necessarily most intuitive, the simplest motion in nature. And rather than put on skates, which I could do, except I don't know where my old skates are anymore, but I'll make do with a razor scooter, which I think they're back. Are they back in vogue? They came and they went and they came. You know, it's always I can never tell. This is an original one. All right. So observations are that when you're at rest on a level surface and nothing pushes you, you stay at rest. And if something does push you, and okay, I can't push myself for reasons we'll come to, but if something does push me, my foot pushed me actually, or the floor pushed me, then you begin to move. It affects your motion in a way that you all are relatively familiar with. If you already are moving, though, the story is different. If nothing pushes on you, so let me get moving. So the story has not started yet. Let me get started, and then the story starts. Ready? Now the story starts. Nothing's pushing on me, and I keep doing what I was doing. I keep going. So that's just an observation when you're skating or you're on something that's basically gets rid of friction. Once you're moving, that's what you tend to do. When you're at rest, that's what you tend to do. Stay at rest. And in the case when you are moving and something pushes on you, now it's more complicated. The push does affect your motion, but it can affect it in a couple of different ways. So this is just laying the groundwork. Okay? Questions at this point? All right. So here are the questions we'll actually pursue. 4 of them. First is why does a stationary skater remain stationary? So why is it that when I effectively become a skater at rest, nothing special happens? And you'd be really surprised if I pulled my foot off the ground and I shot across to the right. It doesn't happen. Second question is why, when you are moving, do you continue? Third is, okay, so why do you need the wheels or the ice? And this is just, it's not yet my introduction to friction, but it's to point out that the world's full of trouble like friction, nuisances that are like friction. And the last issue is, how do you start and stop? So this is, we have looked at the behavior of a skater in the absence of any pushes, but what happens when you do push? Okay, so the first question is, why does a skater remain stationary? And the answer is pretty much a because answer. That it's observed in nature that an object that is left to itself and that is at rest, a body at rest, tends to remain at rest. It's the nature of things in our universe. It didn't have to be that way, but in our universe it is that way. It's just observed. Does it make sense when I say that it's observed? It's not. If you lived in a box with the lights out your whole life, you couldn't know for sure. But if you just go out and watch, and you watch carefully, you'll begin to notice, an object that's at rest tends to stay at rest over and over. Okay? So, first demonstration. It has been the first demonstration for a long time. Uh-oh. I can move the video. And I do it by... Ooh, all right. I do a lousy job as a crew of one. I have to talk, and I have to set the video. It's too much. Okay. Place settings on a table, on a slick tablecloth. And the necessary, right, if I'm going to be doing this at a 3.2 difficulty level. I'm going for 100 points here. So these place settings here are objects at rest, the ones I was just talking about. And it is their nature to stay at rest unless something bugs them. And what I'm going to do is I'm going to pull the tablecloth out from underneath them while bugging them as little as possible. To do that, actually, I need a slick tablecloth because there is this friction, which I'm sweeping under the carpet or under the tablecloth for the day. I'm trying to make friction an unimportant thing. We'll talk a little about that shortly. But the way I make friction as unimportant as possible is I use a slippery tablecloth and I go fast. So friction has very little time to do anything interesting. And what we'll see is we'll see the place settings do what they do. They're objects at rest. We're leaving them alone. They'll stay at rest. Is that okay? This is the concept you know of as inertia. This is physical inertia, not social inertia, political inertia. This is the one that started it all. And for those of you who want to try this, which you can do with or without the glass, okay? It's not hard. All you do is put stuff on the tablecloth. Make sure there's no hem back here, for obvious reasons, because right? And grab the tablecloth far from the table and then come close so that you get some room to get started up to speed before it pulls taut and begins to slip out from underneath the place settings. Last thing is, don't pull up. Pull a little down. All right, I've talked you to death. Any questions about it yet? All right, ready, get set. So it's described as a classic parlor trick, right? I guess in this day and age, if it's not electronic, it's boring. But okay, this was one day, long ago, a parlor trick. It's not a trick at all. It's the opposite of a trick. You see exactly what happens. It's unmagic. Hopefully you understand why that happened that way. This is the way our universe works. And in general, this class is all about giving away the secrets. It's the opposite of magic. So if I do a demonstration and you don't understand why I did it or why it happened the way it happened, I have failed. Right? So I mess up occasionally, and I'll do a demonstration where I sort of forget to put it in context, or I run out of time and I just do it. And you go like, well, that was fun, but I have no idea what the point was. Hopefully I won't do that too often, unless it's a good explosion, which occasionally happens. All right. Questions about this idea that objects at rest tend to stay at rest because it's their nature? Right? There's another version of this demonstration that's important for reasons you'll see shortly. Okay, another object at rest. Apple, right? Yeah, you know what an apple looks like. All right, sharp knife. Nothing is holding the apple in place. I'm going to sneak a knife through it very fast to deal with the friction problem, right? And I will not let go, okay? Yeah, I've done it on that table sometimes, and it's really a little grim for the people in the front row. Okay. If I aim right, this is good. Let's see. Sometimes I manage to get it to stay on the table. Let me try a second. I can make an apple pie. I don't want to smash my knuckles. Ah. Well, you get the idea, doing wheels about it. You get the idea. What held the apple in place? Was anything gripping it? With any forces? Anything pushing on it? No. What concept led it to stay where it was? Inertia. This is inertia in action. That apple tended to stay in place because that's its nature. And if I were really good and I really got a blade to go through fast, I could get the blade through, slice it in half, and it would just sit there, minding its own business. Okay? There's another version of this. Since I'm well equipped today, I'm going to just let go of the apple. There is a nuisance around called gravity In the absence of that nuisance, if I let go of the banana, and suppose there were no gravity, we're out in deep space. And, yeah, sorry. I mean, what can I do? The whole summer I missed you all, okay? Now I get to do my fun games. So if I let go of this and there were no gravity, what would the banana do when I let go of it at rest? It would stay at rest. It would just hover here. So if we could go to deep space as a field trip, it would be great. And I could let go of the banana and it would just be there. And I could slip a knife through it. I can't. I mean, okay, the field trip, it break the budget, okay? I have to contract with Richard Branson for Space 1 or whatever it is, Space 2 or Anyhow, Spaceship 2. If I let go of it, it's going to fall. But if I work very fast, I can make gravity unimportant. The same way when I worked fast over there, I made friction unimportant. So I'm going to let go of the banana, and then, very quickly, I'm going to sneak the knife through it. Hopefully in that order. Okay, ready? Flesh wound. All right. So I did not hold the banana in place. Ready? Okay. Another flesh wound. Man, I'm picking it off. All right. So, but it's inertia that's keeping it there. All right? Second version of inertia. When a skater is moving, okay, we've done a non-moving skater, and fortunately I didn't use skaters for these demonstrations. If you have a moving skater, what's the observation? Well, it's a different one. That if a skater is actually moving across, say to your right, and nothing bothers them, they just keep doing what they were doing. They keep moving steadily across. And that's also considered inertia. It's now the inertia of a moving object. Once something's going, it's observed that it has a tendency to keep doing exactly what it was doing, where exactly what it was doing means to move in a straight line, as we'll see, straight line path at a steady pace. And those two together are the whole story of inertia. Well, I can show you that to conserve bananas here. So I'm going to now deal with a moving banana. I'm going to get it started off toward the right. So the story starts after I let go of it, when I'm not touching it and it's as close to an inertial object as it can be, where inertial means that nothing's pushing on it, and it's doing what inertia had in mind. Now, I can't get rid of gravity again. Gravity's a nuisance. It's going to cause the banana, instead of the banana going straight and true all the way to the wall, it's going to arc, because gravity is going to pull it downward and spoil my story. But if I go fast, gravity again becomes a minor issue. And we'll see pretty much the inertial behavior of the banana. It will move through the knife. So don't blame me. Thank you. And when I do that, please tell me when I make those mistakes, because I record these. We're recording this class, and if you miss a class, you can watch it on the web. And for the past several minutes, you will have, instead of watching me do demonstrations, you will have been staring at that table, okay? So I do this, as I say, no multitask ability. All right, so I'm going to get the banana going, pretty much doing what inertia had in mind, and it's going to be its fault if it encounters difficulties. Ready? Okay? The banana committed suicide. It kept going because that's its nature. Leave it to itself. It does what it was doing. And it simply encountered a knife, kept going. Any questions? All right. This is, then I can give this a name, this observation. Inertia is just the concept. Newton's first law of motion is sort of the official rule. It's a pretty simple official rule, but it is a rule. And it's not an obvious rule. And just to point this out, Aristotle had the wrong view of how motion works 2,000 years ago, and it took essentially 2,000 years for people to learn that, well, no, Aristotle had it wrong. Motion goes like this. Aristotle thought that if you push something, it moves. If you stop pushing, in effect, it stops. And that's not the correct view. It's if you push something, you change its motion. But if you don't push, it keeps doing what it was doing. So the simple version of Newton's first law is that an object that's free of external influences moves in a straight line, and it covers equal distances in equal times. That's the steady motion. So the banana would have, in the absence of the gravity, it would just go like clockwork across the room, straight and true, steady speed. The distance it covers would be uniform. Okay. One other point I know from experience, I have to point out that motionless objects follow this rule too. So an object that's at rest is a special case of a moving object. It's moving not at all, okay? But I think of it as moving. It's just moving not, zero movement. It's mostly a naming and terminology issue. Were you okay? Okay. So, the introductory question. Remember this question? A rotary lawnmower spins its blade, nice sharp blade, whizzes it around over the grass. Can it cut the grass even if the grass has no roots? It's not attached to the ground. Questions about the question? You've seen this one before. Try it again. Again, talk about it among yourselves as you deal with this. I'll give you 60 seconds for it. The grass, as I envision, is just sitting there on the surface of the ground, and the blade comes along. Can the blade come along and slice it? The grass, so it's just like normal cutting grass, except there are no roots. The grass just ends sitting on the surface of the dirt. Okay? 4, 3, 2, 1, 0. Yeah, sure you can. You can cut the grass. It's just like the apple. The blade just comes along. In a rotary lawnmower, the blade comes along traveling so fast, somewhere I think around between 100 and 200 miles an hour, and it's supposed to be sharp, and it just slices the grass whether the grass is attached to the ground or not. Doesn't care. The grass stays in place because that's its nature, and the blade slips right through. And there are mowers that not only cut the grass once, but they recut it over and over, and they chop it up into little teeny pieces. They're called mulching mowers, and their purpose is to try to reduce the grass to such tiny pieces that they just settle into the remaining grass and act as fertilizer, or probably more like smother your grass, but it depends on whether it's sales hype or reality. In any case, you can do it. Questions? All right. Last thing, since we're running, we'll do one more demonstration which you can play with afterwards. Does someone want to be hovercraft pilot here? Please, come on down. So in the absence of friction, if you're motionless, you stay motionless. If you're moving, you tend to move in a straight line at a steady pace. So to get rid of friction, and remind me your name? Shannon. So Shannon's going to sit here and be hovercraft. Just make yourself comfortable sort of in the middle of the and that's on. You hold the press the trigger, and you'll rise up on a cushion of air, and I'll give you a little shove, and you should get going. Just go straight and true, okay? And you're all welcome to try this afterwards. Go for it. See you later. So Aristotle would have understood physics much better if he'd had hovercrafts. Thanks. See you on Friday. Thanks for volunteering.